Imagine tossing a pebble into a still pond. You see ripples, waves spreading outward. Those ripples are like waves of light. But light can also act like a stream of tiny energy packets, photons, almost like miniature pebbles themselves. This strange duality, acting like both waves and particles, is the heart of quantum mechanics. It's as if the tiny building blocks of our universe have a split personality, defying our everyday intuition. But within this seeming paradox lies a world of wonder. Think about how you listen to your favorite radio station. Radio waves, a form of light, carry the music to your antenna. Yet at the same time, this light is also a stream of photons, tiny packets of energy. It's both a wave and a particle, a mind-bending concept, but true nonetheless. Even stranger, it's not just light that behaves this way. Electrons, the tiny particles that power our electronics, also exhibit this wave-particle duality. For years, we pictured atoms as miniature solar systems, with electrons orbiting the nucleus like planets around the sun. However, the reality is far stranger. Electrons don't follow precise paths like planets. Instead, we can only predict the probability of finding them in certain regions of space, called orbitals. Imagine a spinning fan blade. You can't pinpoint the exact location of the blade while it's spinning, but you know it's somewhere within the blurred shape it creates. These orbitals, unlike the neat elliptical orbits of planets, come in a variety of bizarre shapes. Some resemble dumbbells, others like balloons squeezed in the middle. These shapes are determined by the energy levels of the electrons within them. The higher the energy level, the more complex the orbital's shape. It's like the difference between a calm ripple in a pond and a crashing wave, each reflecting a different energy state. Electrons, in their unpredictable dance around the nucleus, can jump between these energy levels. But unlike a ball rolling down a hill, an electron can't exist between these levels. It's like hopping between stepping stones. You're either on one or the other, never in between. When an electron absorbs energy, it leaps to a higher energy level, a quantum jump. When it releases that energy, it falls back down, emitting light in the process. The color of light emitted depends on the energy difference between the levels. Think of a neon sign. When electricity flows through the neon gas, it excites the neon atoms, causing their electrons to jump to higher energy levels. As the electrons fall back down, they release the absorbed energy as light, creating the vibrant glow we associate with neon signs. Each color corresponds to a specific energy transition within the neon atom. Section 4. Schrödinger's fireflies predicting the unpredictable. Now, how do we predict these quantum jumps and the behavior of these elusive electrons? That's where Schrödinger's equation comes in. Imagine trying to predict where a firefly will flit next. You can't be certain, but you can estimate the probability of finding it in a particular area based on factors like light and wind. Schrödinger's equation does something similar for electrons. It doesn't tell us exactly where an electron is, but gives us a probability wave describing its likely location. It's like having a map of the field with areas of higher probability for finding the firefly, represented by brighter regions. The brighter the region, the higher the chance of finding our elusive electron there. Section 5. The quantum symphony of the universe. Quantum chemistry, though seemingly bizarre, governs the very essence of our universe. It dictates how atoms bond, how molecules interact, and ultimately, how life itself is possible. It's a symphony of quantum events, a dance of probabilities and energy levels, all playing out at a scale too small to see yet profound enough to shape the world around us. By understanding the basic principles, we unlock a deeper appreciation for the elegance and strangeness of the universe we inhabit.